Thank you so much. Today we have our gathering for Digital Futures Workshop 2024, Adaptive Kinetic Facade. Actually, I want to mention that, excuse me. Okay. Hello, world. Thanks for coming. Warm welcome to all of you. My name is Zahra Shirzadnia, and I'm a postgraduate of architecture and building technology from Tarbiat Modares University of Iran. And actually, in regards to the motto of Digital Futures workshop, education should be a human right and not the privilege of the wealthy. And this workshop, we aim to demonstrate how to achieve daylight, visual comfort, and thermal comfort simultaneously to enhance occupant well-being through performance simulation and optimization. You will learn how to create a research framework and design adaptive facade with professional level simulation and optimization techniques. Actually, this is our mind map, as you see in the picture. First of all, we have an overview of dynamic facade and then fundamentals of daylighting and thermal comfort studies, and then primary design, the Rhino grasshopper modeling, and then after that, it's actually dependent variables and independent variables are going to be actually showed in the during the tutorial, and then data simulation, view analysis, thermal simulation, and then we start to we're going to start to have an introduction to optimization concepts and common optimization problems and strategies to address them in facade design, and we have multi-objective optimization with Veloci plugin. First of all, we are so eager to have in this workshop Professor Roel loonen. Actually, he is an associate professor at the unit building the physics and service at Eindhoven University of Technology. His research and teaching focus on the development and application of modeling and simulation strategies to provide decision support for design and building that combine high indoor quality with low or no impact on the environment. Actually, many of his projects deal with the advance of adaptive facade and building integrated renewable energy techniques. Thanks for coming, Roel. Actually, I finished my presentation, and it's your turn. Hi, Roel.
Okay, thanks. Thanks very much.
I'm so glad to see you again.
Yeah. Hi, good morning, good afternoon to everyone.
Thank you so much.
Nice to see you, nice to meet you all. I'm going to try to share my screen now.
Yeah.
It says I'm not allowed to share at the moment.
Mm-hmm.
So I think you as a host have to do something.
Actually, I have not seen anything else on the screen. Thank you so much for joining us. Say hello, a warm hello to Habinga. She's the best. Actually, you and Habinga are the best people I ever met.
So in my screen now it says that, so on my presentation at this moment.
Okay. Is it a problem with your sharing your screen? Okay, we can leave the room and then try to enter this room again.
Yeah, but I think you have to turn on something. It says that multiple presenters are not allowed to
Okay.
share.
I try. I think I turn off my actually sharing thing. And please try again. I think because of your
now it's coming. Yes.
Yeah. Because you are a participant, because of that, I should allow you.
Okay, so I think you can see my screen now, right?
Yes, of course, clearly.
Okay, perfect. Yes, so thank you very much for giving me this opportunity to have this talk today. The title of the presentation is Overview of Dynamic Facades, but actually I will do a little bit more in the sense that also I will show some ongoing projects that we have currently at Eindhoven University of Technology in the Netherlands. So the motivation for all of this, and this is not particularly new, I'm expecting, considering the audience for this workshop. But still, what I would like to highlight is the challenges that we have regarding global warming. And especially what I take from this figure is that the longer we wait with taking serious action and drastic reductions in the carbon emissions, the more tough actually it's going to be, the transition. So we need to really have a significant change, and we better do it fast. So if we then look at, are we on track as a building sector? The answer is it depends, and it really depends about what we are looking for. So here in this figure, this is for the European Union. In this case, we are looking at the share of renewables in the total electricity consumption. And then we see on the right-hand side that the dark blue line is pretty much keeping track with what is called in light blue the path towards climate neutrality. So this sounds pretty good. However, when we look at the share of renewables for heating and cooling, then we really see that there is a huge gap, and really call for getting better, for better organizing, on the one hand, reductions in energy consumption, on the other hand, increasing the amount of renewables. So if we know this, then really what comes into the picture is the idea of zero energy buildings. And I would like to argue today also in this presentation that developing zero energy buildings is ultimately incredibly simple. We don't need this kind of workshops actually to learn how to do that, because we can already do it for a long time. However, then we might end up with situations that look like this. So depending on the context and depending on the needs, it can work out well. But obviously, there is more than energy when it comes to designing buildings. And we are becoming actually increasingly aware of the role of indoor environmental quality. So this is about thermal comfort, which I think you will also learn more about later this week. It's about indoor air quality, acoustics, and very important also in the context that we are talking about, visual comfort. So this has to do with the amount of light coming into spaces, which should on the one hand be enough, plentiful if possible, but on the other hand, we want to avoid glare or too much direct sunlight. So very closely associated with indoor environmental quality, we have the concepts of healthy buildings. So that's really the effect of the indoor environment on not just how people perceive or feel about a space, but also their health or absence of sickness, actually. And finally, this can also be closely correlated with financial incentives regarding productivity of office workers, or maybe ability to study, or to perform in general, which often has a much stronger financial benefit than what could be gained by saving energy or reducing energy bills. So then when we turn to building envelope design, there is a large number of criteria that we should care about. So first and foremost, it's providing shelter, protection against rain and wind, thermal storage perhaps. And I'm going to extend this list on this slide. And what I try to do is to think about what would be the optimal configuration or optimal building envelope design for each given requirement. So for these three criteria, maybe we want to build something like a castle or a fortress, maybe. But if it comes to admitting passive solar gains to reduce heating demands in winter, then we may end up with something like this. When it comes to view, also we would like to have something that's very open and transparent. For fresh air, perhaps depending on which place we are in the world, sometimes it's better to be outside than to be inside, actually. And we can keep going. If it's about insulation, then I think the optimal situation often is to have no transparent parts. Privacy, perhaps something like this. So you can see we can continue building this list with almost endless number of requirements, but also when we look at what the optimal situation would be for each case, we see that there's a very large variation. And this is where the challenge comes, because actually we are not optimizing for one of these performance requirements. Ideally, we want to optimize for all of them together at the same time. And this often leads to compromises. So considerations that are somewhere in the middle that makes everybody happy, or we can say makes nobody truly satisfied. And the main reason here, which links to the main topic of the workshop also, is that the envelope, so the properties of the building envelope is fixed. It doesn't change over time, and therefore is unable to respond also to the large variation that we have in terms of weather conditions. So that's both throughout the day. It's also about day-night cycles, and it's about seasons. On top of that, what happens on the inner side of the buildings, also we can have a large variety in terms of conditions. And now the argument is that if we can have the envelope to respond to this in a dynamic way, then we can over time adjust actually what is the optimal configuration to provide insulation in winter, to provide view to the outside when the occupant is there, but maybe to choose for protection during nighttime when there is no occupants in an office building, for example. And with this idea, we can really think about how over time to adjust the building to find optimums in a dynamic way. As you can see from these figures, this idea is not very new. Already for many decades, architects, designers, engineers have been thinking about how to accomplish this. But in recent years, we see with increases in information technology, sensors, actuators, AI, smart materials, everything that has to do with this, we see a range of opportunities arising to move this from a kind of abstract concept to something that is really applicable and doesn't have to be also much more expensive than traditional technologies, but can really lead to a lot of benefits regarding, on the one hand, indoor environmental quality, occupant comfort, on the other hand, energy savings, or perhaps even better CO2 emission reductions. And you can see here we call it adaptive facades. There are a ton of different concepts, different terminology actually out there, where sometimes there are some differences depending also on how systematically these terms are being used. But there's a lot of terminology around this concept that refers to similar ideas. So let me then show you a couple of built examples of these adaptive facades, and I think many of them are probably already known to you. Very famous example in Abu Dhabi, where actually the functionality or performance was really secondary during the design, and making something that looks impressive was the primary consideration. And I think we can say that this goal was definitely achieved. So during the day, different of these shading screens can open and close to block out the sun or to allow views when there's no direct sunlight. Other example, very famous one in Paris, which is of course a lot in the spotlight in the upcoming weeks. These diaphragms or shutter openings can control the amount of daylight that's coming in. So very iconic example, built in 1988 already. We have some more ornamental ideas. So here we can see that the way the adaptation happens really has a huge influence on how the building looks. This is an office building in Austria. This is a building from the EPFL campus in Switzerland, where there's a lot of technologies for daylighting, solar shading being incorporated. And you'll find actually also many publications that study the performance of these technologies. So previous ones was a lot about moving components, sometimes kinetic components. There's also on the smart materials side, there's a lot of developments of how to adjust the amount of sunlight that is entering into a space through electrochromic glazing, for example, that we can control basically with a switch of a button, or can be integrated in a control system. Or there's also technologies that can do this automatically depending on the temperature of the glazing or the amount of sunlight that is being received, so that we have an immediate response to the environmental ambient conditions in this case. And here are a few more, just to give you a flavor, and once you start designing yourself, to also have some awareness of the, let's say the more classical or iconic examples, and the idea that some of these buildings have really been built and they exist, and you can just go and visit them. So I didn't want to make this presentation then only about these examples, but if you are interested in finding out more, you can go to this website with a link at the bottom of this page, where I have been maintaining an overview of, I think it's around 500 examples of adaptive facades. So some are real built, others are more based on material science, or are really more conceptual ideas. So I started this actually in 2010, so already quite a while ago, and I have not been able to maintain it recently, but still it's out there, and maybe you'll find some interesting ideas to develop further. More recently, this overview of case studies of adaptive facades was published as part of the cost action on adaptive facades. You will find the whole book on the website that you can just download for free, with a lot of analysis of different examples of adaptive facades that have been is based on contributions by different experts all around the world. And what makes this very strong is that it's done in a very systematic way. So all the examples that are being provided here, they are described. Here I just took one example according to a detailed systematic approach where you can really make one-to-one comparisons of different technologies, different buildings, and to really see what works, what doesn't work, what has been implemented. Could even do some sort of statistics if you wanted to. So I think this is also very very rich resource if you want to learn more about what has been done, what's available in the world of adaptive facades. Again, the link is in the bottom of the page. And then finally, this is a map developed by Berkeley University, where they so this is a very recent development where they made an overview of state-of-the-art building envelopes, again on a global scale, linked to different climate zones. And also here there is extensive information about different configurations, what has been included, properties, links to further reading. So this is not exclusive on adaptive or kinetic facades, so it's also some more conventional type of building envelope, but still I think also very relevant resource and worth checking out. So then what I just showed is that there are examples, a good number of examples. It's growing a lot. Still, if we look around, then we see that by far the majority of the buildings does not have an adaptive facade. It just has a static building envelope. And this leads to a lot of, I would say, missed potential to reduce energy demand and improve indoor comfort. But there's also a couple of good reasons for that, related to the fact that the design and implementation of these adaptive facades tends to be much more complex than that of regular facades. So it's really moving from the design of an artifact, let's say a static object, to the design of a process, because we are not then only interested in caring about what does it look like, what are its properties, but also how is this adjusted over time, and how the control strategies should be developed. So this is a major point of attention that is not that easily done, but very important. Then there can be some competitive requirements regarding comfort, thermal comfort, visual comfort, and energy, and we need to address them at the same time, again, in this dynamic fashion. It's about short-term actions versus long-term impacts and how to handle them. Even we can think also about maintenance, for example. That's a key thing. Or the last point on the slide is that, we have a lot of benefits of adaptive facades, but it's also clear that compared to conventional alternatives, probably the initial costs are going to be a bit higher, and that needs to be justified. How to do that? So all of these challenges here point to the use of modeling and simulation for providing answers. So modeling and simulation using building performance simulation in this case can be very powerful, because we can create this kind of virtual building model to really experiment with different what-if strategies. So to find correlations between design properties and performance, again, in terms of comfort and energy performance, so that we can demonstrate and communicate these benefits of these facades with clients or other stakeholders. And also we can investigate control strategies, can be simple if-else based controls, or very advanced model predictive control for example, to together at the same time optimize both the design aspects and the control aspects of the technology. There's different software tools available to do that. What all of them have in common is that they were initially designed for or developed these software programs, simulation codes for static buildings with static envelopes. And it can be a challenge to integrate the dynamic aspects of it. In recent years, we have seen a lot of developments in this area. So there's a lot of add-on modules or parametric approaches available to accomplish inclusion of these adaptive components. And for this reason, I'm also actually very happy that these kind of workshops like the one you are attending are being organized to really spread the opportunities and to let a larger group of students and professionals to become familiar with these possibilities. So when we can do that, or when we have this simulation possibility, all these aspects that I show here on the slide. So it's in the center is the indoor environment, which is closely linked to the occupants, but of course also the building construction or the building envelope. That's what we care about today here, in relation to the weather, to renewable systems, to alternative power systems, and of course also very important integration with the HVAC. I think this is an area where there's still a lot to be gained, actually. So my research is actually very much focused also on the integration of these aspects in combination with adaptive facades. And what I try to do, for example, in combination with some of these companies you see here on the right side of the screen, is to allow them to avoid getting stuck in the what is called valley of death. So that is indicated here with a red line. It shows the idea that many good ideas or promising concepts get stuck in a medium level of their development when there is less interest from universities to develop things further, and not yet enough commitment from industry to really see the economic potential and to invest in the final stages of R&D and development. And what I would like to show you two examples of later is to show how using modeling and simulation we can actually bridge the gap from the low technology readiness on the left-hand side towards commercial products that are ready to make an impact in the market. This is a picture of our campus in Eindhoven. The green building is where I'm sitting right now. And what you can also see in the center of the screen is our outdoor laboratory facility where we test different solar energy systems, including also adaptive facade components. Is a close-up. So the laboratory is called SolarBeat, where we have the ability to do full-scale analysis of year-round performance of innovative building integrated energy systems. And one of these systems is it's called the ZISO project, and essentially what this is a window system with Venetian blinds integrated in the cavity. So they are really in between the two layers of glass and can move up and down depending on a control signal. In this case, this has been supplemented with solar cells, so PV cell strips, as we call them, on the outer pane of the glass to transform some of the incoming light that would normally be just absorbed or reflected into electricity that can then be used for air conditioning or for lighting, for example. Now, what is special in this case is that these solar cells, they are bifacial, and bifacial means that they are active both at the front, which is normal because that's the sun-facing side, and at the back, which would normally not be very relevant thing to do in buildings. But in this case, in combination with blinds, so if it's very sunny, we would close the blinds to keep the solar gains outside, and part of that light then gets reflected on the backside of the cells to further boost the energy generation potential of this fenestration system. So we are testing this right now with different combinations of PV coverage ratio, different blind properties, different control strategies to really understand the complex radiation physical principles that are going on here. In this case, we see just one result where the blue line indicates the boost in the energy harvesting potential, which is up to 30% extra, actually. So that's a significant increase, I would say. But on top of these experiments, we are also really looking into models that can be used to further optimize the performance of these systems. So this is using, on the one hand, rhino and grasshopper, ladybug to characterize this type of what is called bidirectional scattering distribution function, so BSDF, to get a full picture of the incoming and outgoing light that hits this fenestration system. And this is then used as an input for radiance, daylighting simulations, and Energy Plus thermal simulations to not only look at the component level, but to really understand also performance at the room level and occupant comfort. In addition, we are doing this type of ray tracing simulations to really see where does the incoming light go, or where does it go, and how can we optimize the configuration then to maximize also the energy generation potential of it. So this is a project that is still running until the end of the year. Results look very promising, and actually already full-scale systems have recently been produced and are now also being tested in the full scale. So we're looking forward to promising results in this area and further development. The other example this is the last example also of today I want to show is at the room level, and this is really related to the idea of changing behavior of the envelope between summer and winter, particularly looking at thermal insulation. So the same way as we people adjust our skin, or in this case, the clothes we are wearing, wouldn't it be interesting to look also if this could be applied to buildings? And actually, this can be done using a concept of active insulation, which is being developed by a startup company here in the region. And what they have or what they propose is what you can see here on the slide. So it's in the middle, simple slab of EPS-based insulation material, and then they make this kind of channels in it. So also what you can see in the middle of the picture. These channels are present at the front and at the back. And then in the corners of it, there is a hole that cuts through from the front to the back, which has a small fan, which is very similar to the fan that you also have in your laptop, actually, that acts as ventilation. Then these panels are sealed with aluminium foil. And then if we turn on the fans, air starts to flow from the front to the back. And this allows us to basically bypass the thermal insulation layer, or to act as a heat exchanger, actually. If we turn off the fans, then we just have a regular insulation slab that maintains the temperature difference between inside and outside. If we turn on the fan, then there are two use cases. One is in warm summer nights when the building is heated up, but outside it cools down, and then we can actually bring that cold outside air, we can use it as a heat sink, basically. So we can cool down the space by exposing it to this cold outside air by bypassing the insulation layer. The other use case is in winter when it's cold and sunny, we can bring in the solar heat gains that are being absorbed on the outside to the inside to reduce the need for heating in the space. So why this works, or why this can be effective, can be visualized by comparing it to alternative solutions, in this case, night ventilation, where if we compare the green lines and the red line, then we see that when we look at the operative temperature, we do not actually see a very large difference. But now when I click and we look at the surface temperature, so this is the indoor surface temperature, or basically the temperature of the thermal mass. With this system, we can really help to cool that down and to have maintained effect that is present over a couple of days, while with the ability to open the window, you can quickly flush out the air, but once it gets warm again, quickly it heats up, actually. So it doesn't really last, unlike this active insulation approach. And we have found this out with the use of simulations in Energy Plus to really investigate such effects in detail. And when we look at thermal comfort in this case, so this is for the summer situation. It's a residential building in the Netherlands where usually we don't have air conditioning. But in this case, on the bars on the left, we can see that around 1,500 hours per year, we would actually have overheating in this case in a well-insulated dwelling. This can be reduced significantly with the help of night ventilation, not so much with shading, but also a lot again, and in the right 3 bars with the active insulation technology. And this can be done, as is indicated here, with much less energy consumption. So the energy costs really go down significantly, which would be very high if we need a big fan to accomplish this night ventilation, which would normally not always be there through natural means. So also here, this is a case where simulations really help to build up the business case to allow us to understand better the performance of this type of innovative systems, and also helps us then to make the next steps towards testing this in a full-scale integration. As we can see here in this figure, for a wall configuration, but also can be implemented into roofs of buildings. We are currently developing this further in the context of a European project where we really hope to make the step towards industrialized, commercially available product. And with that, I see that we already came to over 30 minutes of presentation. So I would like to actually conclude it here. Thank you very much for your attention. Want to wish you a great workshop in the days that are ahead. And of course, if you have questions, then I'll be happy to discuss them here with you. Thanks very much.
Thank you so much. People, if you have any question, please put your comment in chat box or raise your hand and open your camera.
Can I ask a question?
Yes, of course.
Thank you. Thank you so much for your presentation. But in the adaptive facade, for me, the importance is the interaction with the occupants, how we can consider in during the process for the analysis, for the design, and for so on.
How we can incorporate interaction with occupants during the design, you're saying, asking. On the one hand, this is very challenging because often we don't know who but of course we can try to take this into account. And I think that the most important consideration is to always give occupants the possibility to interact or override the configuration of the envelope. There's quite a number of studies available that have looked into, let's say, acceptance or occupant interaction with adaptive facades. But I think that many of these studies have a problem in the sense that the automatic controls that were being considered in those studies, they are rather simple. So that means that there is a lot of need for overrides, because otherwise the configuration that the facade chooses was actually not considered to be optimal. And then these studies conclude that there's this interaction is very essential, but it almost means that the occupant needs to do it himself. And I think that's what we want to avoid. But I think also now with the development of more advanced controls, self-learning controls, there's of course in the AI domain, there's a lot going on that we can actually anticipate what the occupant would want or learn from patterns of interaction to really kind of avoid that they have to interfere too much. What's challenging still is then to predict what would be the energy saving potential, because there's a lack of data in this aspect, I would say. So we don't have a very good understanding of it at the moment, but it's a very relevant field for research. And
And do you have any project working on the climate change to find that, okay, this adaptive facade is work for today, but maybe for the mid and far future is working too or not?
Not an active project, but I'm quite optimistic that having the opportunity to adapt to conditions, whatever that may be, will always lead to at least the same, but probably better performance than what could be achieved with a static envelope. So also in a changing climate, I believe that there's a lot of opportunity, potential for this idea, maybe that can actually become a very strong driver also in the market.
Thank you so much for your presentation.
Thank you.
Anybody wants to ask any question? Okay, Sajade. Yes, please.
Hello, can you hear me?
Yes, of course, clearly.
Thank you for your presentation. I have 3 questions about the Venetian glazing. Number one is, what is the performance and efficiency of the PV? Number 2 is, do you have problem with the temperature of PV that because you have to vacuum the glazing of the BIPV and you can't ventilation. And number 3, how can you produce BSDF files? Thank you.
Okay, thanks for the questions. So the performance of the PV ratio, so how much opaque versus transparent area you leave, and this is actually a big part of the optimization that we're also doing at the moment. So what we are measuring is with 50% and 60% coverage ratio. In my opinion, this is actually already a bit too much solar cells. So this was very much driven by the solar cell people, and for them it's kind of like a solar cell with holes inside, while for say building engineers or architects, the first thing we care about is making that space pleasant for occupants, and then also having the possibility to generate a little bit of electricity. So they are really two different viewpoints, I would say, and in the end we'll probably come somewhere in the middle. To give you some numbers, so if with a 50% coverage ratio, we come to under standard test conditions to something like 100 watts per square meter of PV output. Normal solar panel. That's only for the outside. If we include the backside performance, we can get an additional 20% of boost. So that's yeah, I would say quite promising. Then when it comes to the temperature of the PV, your second question, yes, there is an effect, and the solar cells can get up to 60, 70, 80 degrees. This is going to lead to a reduction in the PV output, and there's not so much that can be done about it. But still, this is a secondary effect. So the effect of having absorbing light, transforming that into electricity will always be what's the number one, and the temperature effect is secondary. There are some concerns about thermal shocks, so having large temperature differences in the glazing area with different thermal expansion, which if it's not done well could lead to breakage of the glass. But so far we haven't seen, encountered this as an issue. And also from the glazing manufacturing perspective, there's a lot of things that can be done with adding additional layers to avoid this. Finally, how to generate these BSDF files. In this case, we do it through the Gen BSDF, I call it library or program. So actually, it's based on radiance ray tracing based on a detailed geometrical file of this glazing system, then using ray tracing to generate the BSDF, and that can then be used in Radiance or Energy Plus for daylighting or energy performance simulations. But thanks for very good questions.
Thank you. I'm concerned about the lifespan of the BIPV, this BIPV, and I think it's lower than others, and it's not efficiency, maybe. But you examine them, and I'm excited to know about this.
Mm-hmm. Yeah, so we have done accelerated lifetime tests, and
Yes.
that did not, that just showed good performance even after simulating 20 to 30 years. So in principle, that's also what is supposed to be the lifetime of the solar cells themselves, which indeed can be shorter than the lifetime of a typical glazed facade. So these are actually things to continue to work on and to develop further.
Yes, thank you.
Okay, any question? Okay, now I have a question right now. You actually present about the PV panels. Actually, it is the engineering doctorate project. And I have a question for the function of the this adaptive facade. The position of the blinds actually effects on the interior and exterior energy. I have a question that how do you explain about the function of blinds based on the energy, because you're using both interior and exterior blinds in the space, and the function actually, because of the function based on the type of season. We have a summer and winter, and when we actually place the blinds in interior place, we have the other function because of the energy efficiency. And when we put the blinds actually at the end of the exterior, outside of the window, we have the other function. And because I'm saying that the blinds reflects the infrared and ultraviolet rays, so it's important that which one of the position we choose. And actually, for this project, you use both sides for the blinds. That's question. First of all, the function about the energy based on the energy, and the other question is about the daylight and about the view, because the view, I think, because the view actually block with the blinds. Thank you so much for your presentation and answer.
Mm-hmm. So for this specific project, so to start with your last question for view, the blinds can be fully raised, actually, so they can be fully up. So then we don't see the blinds. Of course, we still see the solar panels in this case, which is an issue, and that's kind of also what we are trying to optimize. So if you put less solar panels, we have less blockage of the view, but also less electricity generation. What we are now looking at is also the position of the solar cells in the envelope. So there's kind of let's say the view area in the middle of the window where we want to have less cells, and we can shift them to the bottom of the window if we talk about a fully glazed facade, where actually the view is not that that doesn't matter that much, and perhaps also can have a little bit more towards the top. So this is there's some optimization potential in this case. About the position of the blinds, and I think maybe the picture that I showed was not very clear, but the blinds are integrated in the cavity of the glass. So it's a double glazing system with an air gap in between, and the blind is actually in that air gap. So it's neither on the inside nor on the outside. It's really integrated in between. And in this case, we can, yes, still we can achieve a good solar heat gain coefficient or G values. So a lot of the light gets reflected back to the outside, so it doesn't reach the indoor. And then another main benefit is that this works on also on multi-story buildings or high-rise buildings, where often wind loads are actually a main concern, a main reason why exterior shading systems are often not chosen, and that's not an issue with this particular system. So it finds a good trade-off in that sense.
Yeah, thank you so much.
Can you explain for the view analysis which indicator you use it and or which software?
At the moment, it's relatively qualitative. So it's just looking at the amount of moments that the blinds are down, and we look at indicators like useful daylight illuminance, for example. So it's more illuminance based. At the same time, I didn't show you the picture today, but the system has been installed in a real office, so we can actually test with occupants and ask them about their perception. So yeah,
so you didn't use any simulation process to analyze the view to outside or the view to the skies? No.
And yeah, as far as I understand, this depends a lot on the context, actually, where you are, what we can see on the outside, and that determines to a large extent the findings. So yeah.
Some of the articles using, for example, the LEED certification to view to outside, so you have to ground people on movement and the sky, and based on you can analyze them.
Yeah, but that's more a metric of the environment than a metric of the fenestration component.
Yeah. An analysis, okay, is this blind? How much of is this area, and during the time it's blind view to outside?
No.
Okay.
Okay, so let me just say thank you so much for joining us, Roel. It's so I'm so glad to see you again, and it's a very invaluable opportunity to have you in this actually workshop. And we hope that we have collaborated in the future with you.
Yeah, all right. Thank you very much, and I wish you all a great, fruitful workshop.
Thank you so much. People, please open your camera. We want to get shots from the screen. Thank you so much. Actually, with the presence of Professor Loonen. Thank you. Nice people. Okay. 1, 2, 3.